we are, class 37, Friday the 12th of December 2014. Unfortunately, the last day of class. Makes me sad. No. So we'll review for the test today, but we'll mostly focus on, well, at least in the first half of the class, we'll still focus on Green's theorem. And try to encourage you to continue studying it, maybe even over Christmas break, show your family and friends. I've got a few neat things to show you first before we get into that. Some interesting little sidelights here. I found a book on my shelf about partial differential equations. I remembered this, so I looked it up. With an integral you never want to have to do, I think. A hextuple integral. Take a look at that. You can zoom in there. Look at that. A hextuple integral. This is in a partial differential equations book. Probably this function, as is common in partial differential equations, they call the function u, is a solution of some partial differential equation. Hey, look, it's got my favorite Greek letter in there, xi. Integrate that thing, d xi, d eta, d zeta, d omega 1, d omega 2, d omega 3. Oh boy. Maybe it's not as bad as it looks, I don't know. I did do some highlighting there, and evidently we're going to use some sort of spherical coordinates, but that was just for your enjoyment, to see that it is possible to do even bigger integrals over higher dimensional spaces, is what I mean. I also want to show you that I had some fun myself taking one of the functions that we were thinking about a few weeks ago, and we were optimizing it over a cylinder like you have in your take-home, a compact cylinder. And I decided to have some fun myself trying to optimize this thing over a solid sphere of radius 5 centered at the origin. Now with the cylinder, remember, well, first of all, you find the interior points, the critical points in the interior of the cylinder, and test to see whether you have local mins or local maxes or saddle points. And then you also use Lagrange multipliers or cylindrical coordinates to figure out what's going on along the boundary. So you get the side boundary and you get the top and the bottom. But a sphere, its boundary is just one object. It's not made up of different pieces. So how do you do that? I'm not going to go through the details here. I'm going to put this on Moodle, and you can look through it if you like. You can still calculate the Hessian matrix. You can calculate the critical points. Figure out whether they're local mins or local maxes by calculating eigenvalues. I got the answer here. So those are the critical points in the interior of the set. What about critical points along the boundary? You can once again use Lagrange multipliers if you want. Or you can, instead of cylindrical coordinates, you can use spherical coordinates. Here's a picture of what it looks like with the two different kinds of graphs I showed you before. So now again, the function is being defined on the solid sphere that you see. The critical points in the interior I've got in red inside that sphere. And then I've got critical points along the boundary that are all blue. A couple of them sort of have magenta colored halos, though, you see there. I made those magenta colored halos because that's where the global max and global min occur. There's a global max over here on the right and a global min over here on the left. You can also make an animation of the level surfaces as the output of the function increases. This was one of the extra credit type of things on the last exam. And you see those level surfaces moving through the sphere according to those different critical points and ending at the maximum there as C has its highest value. If you consider doing this in spherical coordinates, you have to define a new function using spherical coordinates theta and phi along the boundary. Here's its formula. You can make a regular contour plot of that, although if you do make a contour plot of that, just the light here, you need to realize that because phi is the spherical coordinate coming down from the positive z-axis, phi equals 0, which is this line down here, actually corresponds to 1 point on the sphere, the North Pole, where you're at the top of the sphere. And phi equals pi up here also corresponds to 1 point. It's reversed. It's down at the bottom of the sphere, the South Pole. Phi equals pi corresponds to that 1 point. every other point in here, except for these boundaries actually, correspond to a single point. Actually, these boundaries correspond to a single point as well, but they overlap. This point matches that point over there. Anyway, you can see it's pretty clear the global min occurs right there, and the global max occurs right there. And you've got various saddle points and so forth in between. And some local mins and local maxes. Yeah, actually, I added the critical points to the picture down here. I think this is it here. Yeah, there's the critical points right there. So you need to imagine this as being a picture of what's going on the boundary of the sphere, sort of unwrapped. And again, the North Pole and the South Pole getting expanded somehow to entire lines. And flipped over. This is the bottom of the sphere up here. This is the top of the sphere down there. So it's kind of neat. I really had an interesting graph that I made down here. I tried to graph the function somehow on the sphere itself, and here's what I came up with. Pretty wild looking. Somehow, in a way that I won't explain, that's a graph of the function over the sphere itself. It's actually not exactly right, but it matches as far as a global max being over there, where it's far away from the sphere, a global min being over here where it's close to the sphere, the outputs are lower. There's a local max here and here, maybe a saddle point right about there and there. Okay, so this thing is kind of a funny looking picture of a way you could imagine the graph of that function over the sphere. It's not the function itself, it's sort of a modified version of the function. There's this formula. But I thought it was kind of fun and interesting. All right, so I'm going to make that available for you on Moodle. I also attempted before class today to try to do a numerical calculation of the work done by an object orbiting another object. I pretended the moon had a real eccentric orbit. Of course it doesn't, it's pretty circular, but let's pretend that it was eccentric, and here's the orbit right here. I tried, so this is like the moon and the Earth's gravitational field. I tried calculating the work done by the Earth's gravitational field as the moon goes around the Earth. The work done by that force field on the moon itself. Essentially, I created a function that is the vector field here. And then I created a function that I called work of t to calculate the work as time goes by. It seemed like I was doing it right, but something seemed wrong with this graph. Here's the graph I got. And this is essentially over one period of the orbit. The work starts out negative, well it's 0 because there's no work done initially, but then it becomes negative as the moon is going away from the Earth, and the gravitational field vectors are getting shorter and shorter, and they're pointing in the opposite direction as motion. So this being negative makes sense. This being 0 right there is when the moon was furthest away, and now as it gets closer again, now the gravitational vector field is pointing in the same direction as essentially as the moon's motion. So it made sense that it became positive, then it becomes real positive here as the moon starts traveling really fast, coming down to the closest point of approach. It's 0 when it is the closest point of approach, and then it becomes negative again, and it's still going kind of fast. But it didn't make sense because this was one period, yet this value didn't come back to where it started, and it should have, because it's conservative, and you're going around one loop of the orbit. So I'm not quite sure why that came out to be the way it is. Maybe it's related to the fact that the function is undefined at the origin. The force field is undefined at the origin. I'm not sure. I was perhaps thinking about it in the wrong way. I was trying to make a graph of the work done. This doesn't seem right to me. I'm going to try to fix it at some point and get it back up on Google too. But that can relate to thinking about the work done by a force. All right. Still want to focus on Green's theorem for a bit here. So again, here is the vector field. Same vector field as from Wednesday, and our Daniel Jacobson, the one who gave me this tie short after today, so the other class. So I'm wearing his tie today. You don't see him, but you'll watch this 50 years from now and realize you were there. What I'd like to do here now is show you something interesting. Well, try to help you understand the Green's theorem again. And I'm still wearing green today. I added something to the animation from Wednesday that I didn't have in it before. I added two things actually. I added a contour map to this picture in addition to the vector field in the string plot. I also added that. What do you think that is? It's a little tiny paddle wheel. It's a little tiny paddle wheel in this fluid flow. That's what we're pretending, right? Thin sheet of fluid, maybe 1 molecule thick. I don't know. Is that possible? I don't know. Get 2 glass plates, put a thin sheet of water between them. You effectively model the fluid flow with a 2-dimensional vector field. It's a velocity vector field. The vectors tell you the velocity of any water molecule as it passes through that point. Like right there, say, any water molecule that passes through that point at any given moment in time is going to have that velocity vector. Of course, let's scale down. True velocity vector is longer, but it's pointing in that same direction at that moment in time. That's the velocity with the given length. That's the speed. The blue curves, again, are the stream lines. You make them a stream plot. They are showing you the paths of the water molecules. You don't worry about how realistic it is here, since if you're after realism, take fluid mechanics. But what we're wondering is if we took a little tiny pinwheel here, a little tiny paddle wheel, and took a pin and pinned it in there, we're wondering how would it rotate. And actually I picked my starting point to be at a value of the scalar curl that's too far negative. Mathematics capabilities for making smooth animation kind of go haywire there. Again, what I do have here is the contour map of the scalar curl. And you can see the value there along this contour is about -11. Let's move the paddle wheel this way, and the value of the scalar curl will be closer to 0. I can grab this. I've set it up with the locator command to be able to move that. That's part of the animation. And I can move it down to, say, right here, where the value of the scalar curl is -1. And if I change theta, watch what happens. I get a little rotation action there. And it's a clockwise rotation, corresponding to the fact that with the scalar curl, a positive rotation is counterclockwise because of Green's theorem. Let's write down Green's theorem again. I don't have any green chalk today. Sorry, I gave it back to Dr. Wesley. He's the one with green chalk. Again, Green's theorem is a theorem, so of course you've got hypotheses. Your function must have continuous partial derivatives. You are assuming, in the simplest case, that you've got a simple closed curve that's oriented counterclockwise, bounding a domain. You read about, or should have read about, situations where the domain might have holes in them. And in those situations, you actually have to orient the inner circle or curve in a clockwise direction to make Green's theorem work. Got some completion problems you can do if you're interested in that. We're not going to focus on that harder case. We've got to think about those two curves, and domain becomes a bit more complicated. And we're just going to think about the simplest of all cases. Again, it tells you that the line integral of the vector field around the simple closed curve oriented counterclockwise, which I emphasize by putting the circle and the arrow in there. I think my program that I used to make tests, though, doesn't allow me to put a little arrow in there. So on the test, I might just put a little circle, just like the book. But that thing equals the double integral of the scalar curl over the domain D. I Again, the scalar curl equaling derivative of the second component with respect to the first variable minus the derivative of the first component with respect to the second variable. All right, so because of the counterclockwise orientation you see here, and the signs here doing it in this order as opposed to switching it around, a positive scalar curl corresponds to the little paddle wheel going counterclockwise. That's the positive orientation. And a negative scalar curl corresponds to the little paddle wheel going clockwise. Here we're at a negative value for the scalar curl. If I move this point over to a spot where the scalar curl is positive, the rotation will change to being counterclockwise. There we go. You can see, well, it's kind of herky-jerky here. Let's pause this and try to start it over. Over here, the scalar curl is positive, so we get a counterclockwise rotation. Now you see it. Why, again, is it rotating? It's real small. Pretend it's even smaller than what you see there. The vectors in the vector field are approximately constant on either side. They're about the same, but they're ever so slight differences in length. Enough to make this one would be a counterclockwise rotation. Evidently, the velocity vectors of the water molecules are perhaps a little longer over here than they are over here. And negative when we were over here, that was a clockwise rotation, so when it was right about there, the vectors going this way are a little longer than the vectors going this way over here. On one side of the little paddle wheel or the other. If I put this at a spot close to where the scalar curl is 0, like right here, see a little 0 there? If I move the paddle wheel there, then it's probably not going to rotate. So now we see the theta changing. You can think of theta as effectively time. Now we don't see any rotation in the little paddle wheel. Actually, it might be rotating slightly because that might not be exactly on that curve. Probably not exactly on the curve. But it's such a slight rotation you can't see. Why does this work? If you want to try to work at developing some intuition about this, again, this thing is called the circulation of F around C, this oriented curve, oriented counterclockwise. Actually, the circulation, again, doesn't have to be a counterclockwise rotation. It could be a clockwise rotation. However, for Green's theorem, as a standard way of writing it, you make this counterclockwise and you make the difference go this way instead of the other way. If you did make this a clockwise rotation, then you'd have to switch these around or put a negative sign in front of it. Again, the way to make sense of this is to imagine that C is really small. So small you can barely see it. You have to use a microscope or something. And then in that case, the scalar curl is approximately constant. Okay, here's the symbol for that. Take a sample pointing there, P. Approximate this integral as that constant value of the scalar curl. I'm pretending it's constant. Over this domain here. P is this one point in that domain. If the domain is really small, because the scalar curl is continuous, I'm assuming these partial derivatives are continuous, this is going to be a good approximation. Times the double integral of 1, which is going to be the area of D. Telling you that in a limiting sense, as this domain gets smaller and smaller, you can think of the scalar curl as being a circulation per unit area. Where a circulation in this sense makes sense because you can relate it to these spinning paddle wheels. And you can also bring some physics into play, as the book does on page 1007, when you have those two boxes. On 1007 to say that you can also say the angular velocity radians per unit time, like radians per second or something. 2 pi radians per second would correspond to the paddle wheel making 1 revolution counterclockwise in 1 second. 4 pi radians per second would be 2 revolutions in 1 second. It's got a sign. Negative pi radians per second would be a clockwise rotation half the way around in 1 second. That's angular velocity equals 1/2 the curl. So 1/2 comes into play. You can see in the derivation in the book. The angular velocity of the paddle wheel. It's got to be a tiny paddle wheel, pinned at the point P, equals this, or at least is approximate to that. And the approximation will get better and better the smaller the paddle wheel gets. Of course, there's friction and that kind of thing to think about. We're thinking about this stuff without thinking about friction. So because of that, in a sense, you can think of the total circulation of F around the entire curve, which I haven't shown you yet, I haven't done the circle, as sort of being found by adding up. Think of the integral as adding up the little circulations. The curl times dA, since a curl is a circulation per unit area, is measuring some sort of circulation. You're adding up those little circulations to get the total circulation. That's the intuition. Yeah, I'm not an expert in fluid mechanics. Talked to Professor Stein about that. You know, I don't know how, there's some flows that are going to be more realistic than others. If you can make a realistic flow, then you're going to have this be true. You're going to be able to measure the total circulation around some bigger curve as a sum of the small circulations around tiny little curves. And Green's theorem is true in that sense. You might wonder, well, why do you really want to measure the circulation around some closed curve? I don't know what the actual application might be of doing that, this particular circle right here. Why would you want to measure the circulation around that? So I'm not sure of the applications of that. Evidently there are some. But again, you should, on the final exam, you should be able to estimate by looking at a picture like this, and it's going to be a static picture, of course, on the final exam, whether the circulation is positive, negative, or perhaps close to 0 here. For the most part, is the vector field going against or with the direction of the oriented curve? Counterclockwise. Certainly along here, you look at the blue lines, we're going against the flow. So that's going to contribute negative values to the integral, the circulation. We're continuing to go against the flow over here, more negative values. It's only when we get right about here or so, there it looks like the velocity vector is going to be tangent, orthogonal right about there to the velocity vector of the curve. And then we get positive contributions in here. It's hard to tell right here. I guess it's closer to there where it's maybe positive than it is to that. We got some positive contributions over here, close to 0 contributions in here. Looks like negative contributions over here for the most part, close to 0. For the most part, we should expect negative contributions to the integral. We get a negative integral as indicated by the fact that this orange graph is negative in these areas of below the horizontal axis. This curve has a negative circulation. The vector field has a negative circulation with respect to this particular curve. I don't claim that I have a complete understanding of this. It's pretty clear, and I'm sure you don't, and many people don't. I think you can always learn more about this stuff. You can always consider other examples. And to tell you the truth, that's one of the main things I'm looking forward to doing in paradise with the Lord, is spending time learning more about Green's theorem and other theorems, okay? The universe and the remade universe in the future is really infinitely complex. There's infinitely many things you can learn, I think, and I look forward to doing that in the new creation. I hope you do too. And over this Christmas break. Show your family. All right, we should spend some time thinking about the final exam now. And I'm going to start thinking about the final exam, actually, by continuing to think about chapter 16 and 17. So let's look at that list of problem types that I sent you. I haven't written the final exam, so I'm not absolutely positive these are going to be the exact questions. I might make a few tweaks here and there. As it stands, it's currently what I'm planning. Probably it won't change. So you saw these different types of problems. What I'd like to do in the time we have remaining today, about 25 minutes here, is I'd like to focus on what I mean by saying this final exam is going to be more conceptually focused than computationally focused compared to the midterms. Of course, there's going to be plenty of computations on this final exam, but there's also more conceptual problems where you need to think about ideas geometrically and know terminology like this stuff here, like chapters 16 and 17. Vector line integrals, circulation, path independence, potential functions, scalar curl. I should have put the word conservative in there. Conservative vector fields. I should have added that. You want to know the relationships between all these things. It might be helpful to draw some kind of diagram even. Let's get you started in thinking about this. First of all, what's a conservative vector field? Again, I should have put that in there. A vector field is conservative if it's the gradient of some function, some potential function, on some domain. Conservative vector field. This is on some domain. I'm not saying whether the domain is simply connected or not. I'm just saying it's some domain here. Conservative vector fields are very special. First of all, before I get into that though, just like I emphasized that dot products are always numbers, you should also never forget that gradient vectors are always vectors. In fact, every time you say the word gradient, it's good to add the word vector on it, like I did just there. Gradients are vectors. They're gradient vectors. So anytime you see a symbol like this, even though it's not traditional to put a half arrow above that, it is a vector. So if we've got a conservative vector field, that means there's some function v whose gradient is that vector field. And those are very special. One property they have that's very nice is line integrals of conservative vector fields are independent of path. Start at a point P, start at a point, end at a point Q. Then we have an oriented curve. We do the line integral of f over that curve. We get the same answer no matter what the curve is. We get, in fact, v of q minus v of p. Just like antiderivatives, potential functions are determined up to additive constants. There's really infinitely many different potential functions you can pick. Add any constant to any given one. This difference, though, those constants are going to cancel out. You're going to get the same thing no matter what when you integrate this vector field, this conservative vector field, over this oriented path. If it's closed path, so that P equals Q, doesn't matter whether it's counterclockwise or clockwise here, the integral is going to be 0 because v of q minus v of q will be 0. So that's independence of path. That also means, in terms of circulation, I should put the word circulation in here too, that the circulation for a conservative vector field around some oriented closed curve is going to be 0. Which makes sense because of this cross partials condition for conservative vector fields. Remember that? These two things are equal everywhere in the domain for a conservative vector field. Let me mention that now and write it again. The fact that f is the gradient of some function on the domain means the partial of f2 with respect to the first variable will equal the partial of the first component with respect to the second variable on the entire domain. Therefore, the scalar curl is always 0 on the entire domain for a conservative vector field. You can also use this implication to say that if these cross partials are not equal over the entire domain, they might be equal at some points, but if these are not equal functions, then you can say f is not conservative. There is no potential function. It's called the contrapositive of the original statement. If this is true, then that's true. So if this is not true, then this is not true. The converse of the original statement, if this is true, then that's true, is true under an extra condition. What was that extra condition? I mentioned the word 2 minutes ago. It's 2 words, actually. SC. Simply connected. The converse, if this is true, then that's true. If these are equal on an entire domain, then f has a potential function on that entire domain. That's true as long as you assume the domain is simply connected. What does that mean? Well, the book describes it in terms of shrinking curves down to points. However, in 2 dimensions, it's effectively equivalent to the domain not having holes in it. So this domain that I'm drawing right there with a hole in it is not simply connected. It doesn't have to be a big hole. It could be just 1 point missing. Imagine that's just 1 point missing. That's not simply connected. That kind of idea doesn't work in higher dimensions. If you take 3-dimensional space and you take away 1 point, or take away an entire sphere, solid sphere, actually the remaining set is still simply connected. Because as far as shrinking the curves to points, you can sort of go around the missing point or missing sphere. You can avoid it, you can still shrink it to a point. So that idea of not having holes doesn't work in higher dimensions. What would be an example of a non-simply connected domain in 3-dimensional space? Take all 3-dimensional space and take away one of the axes, like the x-axis. Take it away. The new set created by taking away the x-axis is not simply connected. So if you had a curve going around the missing axis, you cannot shrink that to a point. Anyway, we're only going to worry about 2-dimensional examples. So for us, this is the typical kind of thing. 1 point missing, maybe 2 points missing. Maybe the entire plane except for 1 point would be the domain. That would be a not simply connected domain. This implication doesn't work the other way when it's not simply connected. The book gives you an example. Vortex vector field you should have read about. That's an example where this cross partials condition holds, but it's not a conservative vector field over the entire domain. It is over simply connected subdomains, but not over the entire domain. Read about that if you're not sure what I mean. It's in section 16.3 especially. What else? Anything else here? Yeah, one more thing. You shouldn't forget how that intuitive way of deciding whether a certain line integral, whether it's a circulation or not, is positive, negative, or close to 0. Say this is the curve you're integrating over. If your vector field, for example, looks like this, just sort of drawing these somewhat randomly, not completely randomly. Do you think the line integral over that oriented curve, oriented counterclockwise, is positive, negative, or close to 0? Somebody must. Go ahead. Okay, that's a guess. I'm going to say it's definitely negative. Maybe I should have phrased it as definitely negative, definitely positive, or maybe real close to 0, so it's hard to tell. This is definitely negative because the orientation of the curve is counterclockwise, and for the most part, these vectors are opposing that motion, so to speak. The projection of those vectors in the vector field F along the the tangent vector, which goes counterclockwise, is mostly going to have negative components. Definitely the line integral around this particular oriented curve is negative. Is there a way to tell if it's 0 for sure? Actually, if you knew all the vectors in the vector field were orthogonal to the curve, like I'm trying to draw here, that would imply that the answer is 0. If it was clear from the picture that you mean for these vectors to all be orthogonal, normal to the curve, then the line integral around that curve would be 0. If it's definitely not a 0, then that can't possibly be a conservative vector field. That's an example of a conceptual question that comes up as well. All right, let's move on. Number 2 here is pretty computational. Just calculate a partial derivative. Okay, it's not going to be the easiest derivative in the world. I think if I recall correctly, it's got the quotient rule involved, for example. So don't forget your calculus rules. Use your sheet of paper, but you know, the quotient rule is something you really should remember anyway. This one's kind of a mixture of conceptual and computational. What do I mean by this? There's a problem where you need to find a formula for a linear function whose level curves are given and labeled. The level curves of a linear function are going to be straight lines. That should make sense if you think about the three-dimensional graph of a linear function. It will be a plane. If you cut that plane with other horizontal planes, it'll intersect it along straight lines. And the level curves in the xy plane will be the projections of those lines down into the xy plane. Pretend they look like this. They should also be equally spaced if you've got a constant contour interval. Remember, that's how you're choosing the particular level curves that you actually draw. You're making the outputs of the function vary by a constant as you keep going to the next level curve. Actually, I meant to draw this so it goes to the origin. Which means this needs to be a little further down. And this one maybe should be a little higher. I'm trying to make them equally spaced. Pretend this is z equals 2, z equals 5, z equals 8, z equals 11, z equals 14. Those are the outputs of the function along these curves. The contour interval, sometimes called m here, is 3. Though I think I'm going to erase that because I'm going to use m for something different now. What linear function z equals L of xy is going to have these level curves as the level curves in its contour map? It's a linear function, so you should be able to write its formula like this for some m and d. As I've drawn it so far, you can only find one of those three numbers, m, n, and d. Which one can you find as I've drawn it so far? With the information I've given you so far, here's a hint. This one goes to the origin. Want to say? D. And what does d equal?
5.
5, yeah, because it's the output of the function when x and y are 0 at the origin. It's this level curve. The output is 5. So d must be 5. So that's nice when the graph goes to the origin. If it doesn't go to the origin, it gets a little harder. What are m and n? With the information I've given you, you can't determine it so yet. However, if I, for example, gave you this x-intercept, say it's 5, and this y-intercept, say it's 2, that is enough information to find m and n. A couple different ways you can think about it. You could plug in this point, x equals 5, y equals 0, into L, and set it equal to 2. Solve for m in that case. You could plug this point in, 0, 2, for x and y, set that equal to 2, and solve for m. Plug in particular points. Also, if this point didn't happen to go through the origin, you'd have to know some other point. You know, maybe you know this point here is the point, -2, -2 or something, plug that into the function, set it equal to 11, that would allow you to solve for D if you did not have a line that went through the origin. You'd have to know M and N though. You probably want to solve for M and N first, based on these two. Well, okay, I guess you get a system of equations because you have D still in those equations too. You get a system of equations that you have to solve. So it's definitely easier when it goes to the origin. You also can think of M as being the constant value of the partial of Z with respect to X. Makes sense? It's a linear function that's going to be constant. And you can think of N as the partial of Z with respect to Y. And use these 3 points and their outputs to figure those out. For example, partial Z partial X is going to be the same as delta Z over delta X. As you move from here to here, Z goes down by 2, its change is -3, and X is going up by 5. So M is going to be -3/5. I'll let you figure out N on your own. I'd encourage you to try another example, make up another example on your own. It's not too hard when you see the idea, but I know sometimes people have a difficult time with that type of problem when they don't see the idea. Number 4, there is a problem where you need to find the angle between 2 given planes. I'm going to let you look that up, how to do that. I believe there was either a completion or graded problem where you did that. I'll let you look that up. Long problem, like on exam 2, calculating the curvature, unit tangent vector, unit normal vector, oscillating circle, velocity and acceleration vectors, and tangential and normal components of acceleration. Long problem worth 20 points. So you had one like that on exam 2. So you want to review that one. You want to make sure you can use all the formulas related to these things. The only formula you don't want to use is you don't want to use the definition of the unit normal vector as the derivative of the unit tangent vector divided by its length, because it's too nasty. Okay? If you ever try that by hand, if you have tried it, you realize it's just too painful, even in fairly simple examples. So instead, what you want to use is you want to use the trick that works in 2 dimensions. This doesn't work in 3-dimensional problems. Say you've got a 2-dimensional parametric curve where the orientation is from right to left, like this, say. And let's say at this point you want to find the unit tangent, unit normal, etc. The unit tangent would be like that. Unit normal is orthogonal to the unit tangent. Does it point northwest or southeast? Guess wrong. Northwest. It points toward the center of the oscillating circle, which you can think of as a circle about like this. It's a circle that most closely approximates the graph at the given point. The center of the oscillating circle would be up here somewhere. The trick, remember, is to take the components of t, which I'll just call a and b, and switch them, but also put a negative sign in front of one of them. It could be the first one, it could be the second one. You have to decide which one it is based on the picture. Now, if your picture looks like this, a and b are going to both be negative in this case, because t is pointing to the southwest. You want n to point to the northwest, so you want its first component to be negative and its second component to be positive, which in this general setup means you need a negative sign in front of the second one, so that it's positive. Since a and b are negative, well, since a is negative, negative a is positive. And you want that second component to be positive because it's pointing upward, not down. All right? If the curvature was like this, then the unit normal would look like that. For the same a and b, this would be negative b comma a. Once again, your tangent vector word ab. So you've got to draw the picture to make sure you get the direction right. If you can't draw the picture accurately by hand, use your parametric mode on your calculator. Practice that if you've never practiced that, parametric mode on the calculator. I hope everybody's tried that. That's something to make sure you can do before the test. If nothing else, to get capital N right, which does affect everything else, by the way. You know, finding the normal component is going to be important. You're going to have a correct capital N. All right, how about this one? There's a problem where you need to estimate partial derivatives at points when you are given level curves of the function. This one, there's no formulas. And in fact, this picture with the level curves, I've taken out of a book in the past, and I'll do that again. It's not a picture that I make with Mathematica. And it's kind of an odd-looking picture, actually. I don't remember exactly what it looks like, but it looks something like this. It's got some ovals. But these ovals are kind of centered in a strange way. Something like that. This is not necessarily the exact picture, but it's something somewhat similar to this. And you pick a few different points. Maybe there, here, and here. I don't remember for sure what that picture looked like. It's sort of like this. And you try to approximate, not in a numerical sense, but in a sign sense, positive, negative, or close to zero, the partial derivatives of the function whose level curves look like this at these 3 points. So you need to imagine letting x increase and letting y increase at the points, and based on the labeling for the level curves, decide which of those are positive partial derivatives, which are negative, and which ones are zero. This one should be close to zero because that's horizontal, got a horizontal tangent. So even though as you move to the right, the function value increases, instantaneously speaking, the rate of change, the instantaneous rate of change of the function at this point in the x direction is going to be zero when a horizontal line is tangent to the curve at that point. This one will be positive, this one will be positive. Partial with respect to x for this one's going to be negative, right there. This one's hard to tell. I guess this one would be positive because there's sort of implicitly some other level curve that's not drawn in there. At z equals 1.5, say. Actually, I guess that means it's negative. Did I say positive? Partial with respect to z with respect to y, there would be negative. That's the kind of thinking you're going to want to do. And you're also going to want to think about the fact that partial derivatives are further away from zero when the level curves are closer together than when they're further apart. The gradient vectors are longer. When they're further apart, the gradient vectors are shorter. The partial derivatives are closer to zero. Positive or negative. That's something else you want to think about when you think about this picture. Number 7, that's a calculation problem. Use a parameterization. You do need to come up with a parameterization. It's either going to be a circle or a line, so you should practice parameterizing circles or straight lines. We've done that before. There's a change of variables problem involving integrating over a parallelogram. That's a computational problem. I will give you what the change of variables will be. U equals something, B equals something. Or maybe I'll give it to you in terms of x equals something involving U and B, and y equals something involving U and B. That's the nicest way to write it, actually. The main thing you'll need to do there is calculate the Jacobian determinant correctly, and then do the integral calc correctly after that point. This one here is conceptual, number 9. Oh, we're almost out of time. Based on a parametric curve and some level curves, geometrically interpret and estimate the derivative that comes from the chain rule for paths. Like, pretend this is the level curves for your function. Pretend you've got a bug moving through a plane. These level curves represent the temperatures, perhaps. And you want to estimate the derivative of this function at various points. The bug is moving in this direction. It feels the temperature change. For example, at this point, maybe at this point, and at this point. You can use the formula for this to help you figure it out. It's a dot product of the gradient vector dotted with the velocity vector, which can also be thought of as the length of the gradient vector at the given point times the speed, length of the velocity vector, times the cosine of the angle between those vectors. These things all depend on t. Right at this point, the gradient vector looks like this, and the velocity vector is basically the same direction there. Maybe slightly different. The dot product will be 0. Not 0, positive. The angle would be between 0 and 90 degrees. Cosine would be positive there. Here you'll get a negative 1 because the gradient vector makes an angle bigger than 90 degrees with the, here's the gradient vector, here's the velocity vector, like this. Angle there is bigger than 90 degrees, you'll get a negative rate of change, which makes sense. The bug's going from hotter to colder. What about right there? What do you think it is there? Something special about this curve there, it's tangent to the curve, to the level curve. The unit tangent's still going to look about like that, but now the velocity vector looks like that. Right angle. Cosine of 90 degrees is 0. You get 0 at the point where they're tangent to each other. Real quickly, 10 is computational. 11 is draw the domain and do the integrals in 2 different ways. One is a vertically simple region, one is a horizontally simple region. D is going to be a certain triangle, you're going to have to draw it accurately. 12, you'll need to find a potential function and use the fundamental theorem for conservative vector fields, which is to do the integral by doing this difference. So it's pretty easy actually. And then one problem where you use Green's theorem to calculate a circulation as a double integral, and you'll want to use polar coordinates to do that integral. And there's also going to be an unspecified extra credit part of that problem. And I will leave that just to, I won't tell you what it is. Hopefully if you study enough, you'll get it. It's not much, it's like 3. Yep. That's the plan at the moment. I might tweak a tiny bit, but I doubt it. This is probably that's it. Yeah,